Hello everyone, so this is your experiment 6. Experiment 6 is on RC circuit. I actually don't know whether you have completed RC circuit in your theory till now. If you have completed, it's fine. If you haven't, you will complete the theories in the theory class itself. I will not be going into details, going into details of the theory. I'll just be talking about the circuit itself. Now, there are three kinds of passive components that we use in a circuit. We have resistor, we have capacitor, and we have inductor. Here the capacitor and inductor are energy storing elements. What that means is these two elements can store energy. The capacitor stores energy in form of voltage. The inductor stores energy in form of current. So this is the basic that we need for this experiment. Now, since our experiment is regarding RC circuit, let us draw an RC circuit. We have a switch here, we have a resistance here, we have a capacitor here, and this is our ground. So this is our R and this is C. So suppose this voltage is V in. Now what capacitor does is capacitor stores energy in form of voltage. That is, if this switch is switched on, what happens? This current will flow through this circuit and the capacitor will be storing charge. The capacitor will be storing charge, and the capacitor will keep storing charge unless the output voltage of the capacitor becomes equal to V in. Once the output voltage of the capacitor becomes equal to V in, then the circuit becomes open circuit, because at this node the voltage is V in, at this node as well the voltage is V in. So no current flows through the circuit any longer. So this is how charging phenomena takes place. Now this storing of charge, or this change in voltage Vc into V in, does not occur instantaneously. What happens? Suppose at initial condition our switch was off. At initial condition our switch was off. So our input voltage to the circuit was 0 volts. Input voltage to the circuit was 0 volts. In switch is on, there is no voltage across this R and C, and no current will flow through it. Now at a certain time t, we turn the switch on. Then what happens? The voltage level will shift abruptly to V in. And again, after a certain time, we again open the switch. Then what will happen? The voltage level at this node will again become 0 volts. So by switching on and off, we get a pulse from 0 to V in. Now what we have learned so far, or what I have told you so far, is that this voltage will get stored into this capacitor till the time that Vc is equal to V in. So what happens is, when the switch was off, the capacitor was discharged and the voltage across capacitor was 0 as well. When the switch is on, the capacitor will start getting charged, but because of presence of this resistance, it will charge slowly. So at one point it will reach the peak. See here, the voltage does not instantaneously change to V in. Rather, this is the curve of Vc. It gradually increases to V in. Then again, when we switch off this switch, the capacitor discharges through the resistor, and as a result, the voltage gradually decreases to 0 volt again. So this is our capacitor voltage. Now the curve that you see here and here, these are exponential curve, and the expression of this curve, since this is a curve of Vc, the expression of this curve Vc is equal to V in, which was the initially charged voltage, into e to the power minus t by tau, that is exponentially decreasing. Now what is this t? This t is the suppose you are taking VC at this point. So this T is the time difference between these 2 points. That is why when the capacitor starts to discharge to the point of consideration, and this tau is called time constant. So in your theory, you'll be learning that tau is equal to RC. So time constant is equal to RC. So how tau is equal to RC? This is not our concern at this moment. Our concern at this moment is this equation. Vc is equal to V in e to the power minus t by tau. And we want to check whether this expression is correct, and we want to simulate this and obtain a graph like this. So let's do it. Let's see. So we open our schematic. From schematic we need okay, what do we need here? See, if we go here, we need a voltage source and a switch that will give us pulses. So instead of doing that, we have pulse sources available in PSpice. So let us take pulse sources. From here we choose part and choose V pulse. So we have V pulse. This is our pulse source, and from here we again choose R, which is our resistor, and we again choose C, which is our capacitor. I am rotating the capacitor using Control R, which is the shortcut, and again we need a ground. So here we have ground analog, and we make our basic connection. Okay, now after making our basic connection, we keep the resistance value is equal to 1K as it is. We change the capacitor value. We change the value to 1 micro. And this IC over here, it's not necessary to put a value to it, but we will. This IC means initial condition. It will indicate if the capacitor was charged initially or not. So we would put IC is equal to 0. So initially the capacitor was not charged. We press OK. Now we have to model a voltage source V1, so, which is a pulse source. So we double click it and we'll put DC is equal to 0, AC is equal to 0. Our V1 will be the bottom limit. So here if we observe this graph, our bottom limit is 0 volt and the top limit is V in. Let us suppose V in is equal to 10 volts. So our bottom limit here is 0 volt. Our top limit V2 is equal to 10 volts. The next thing is time delay. TD means time delay. What does what time delay means? Time delay means that you're getting rectangular pulses. That is, from a V pulse you'll get pulses like this. So pulses like this. So the time delay means after how much time will the pulse starts occurring. So this time over here is our TT, time delay. So we want the pulse to occur right at the beginning. So what we do here is we place TD is equal to 0. Then we have some other parameters, TR and TF. What are TR and TF? Ideally the pulse is supposed to be like this, that is, it goes abruptly up and then it comes abruptly down. But practically when you apply in a circuit, the pulses are little skewed. That is, they don't go up abruptly and they don't come down abruptly. So this time over here is T rise time, TR, and this time over here is TF. TF is fall time, TR is rise time. So ideally TR and TF both should be 0, but in this case, in case of PSpice, since it's simulating the circuit, we cannot put this as 0. So we put this as 0. Suppose 0000001. We are putting a very small value, so such that it's equivalent to 0, and we save attributes. then TF is also equal to we copy it and we paste it. In case of TF, we want TF to be almost 0 as well. Now two more things are there. Those are pulse width and PER. PER means period. Now what is pulse width and period? You see the pulse here. This is the amount of time when this is the amount of time when the entire when the pulse would be on, and this is the total period of pulse. That is, total period of pulse is from this point to this point, and the time when pulse will be on is this 2 point. So this is called, this portion, this time over here is called pulse width or PW, and this time over here is called PER or period. So in our lab sheet, when you see lab sheet, it said that we will use the square wave of period 100 Hertz. So since we'll use period 100 Hertz, this is given in terms of seconds. So if the frequency is 100 Hertz, what is the time period? Time period is 1 by 100, and we want for half of the time the pulse to be high, that is 10 volts, and for other half the pulse to be 0 volts. So our pulse width would be half the period. So if period is 1 by 100, our pulse width would be 1 by 200. So we are saving this attribute and we are pressing OK. So our circuit preparation is done. Now we want to see the input voltage here, which will be a pulse, and output voltage here, which would be exponentially rising and falling. So we take our voltage node, we place one here and one here. Okay. After that, our schematic is done. We save the schematic. I'm naming it RC. Then what we do is we go here, setup analysis, we click here, and there are lots of points in setup analysis, but we will choose transient. Why transient? Transient means dependent on time. So if we see this graph over here, the initially voltage was 0, then after certain time switch was turned on and voltage became Vin. After certain time switch was turned off and voltage became 0. That is, in the x-axis we have time. Whenever in PSpice simulation we have time in the x-axis, we use transient type simulation. Transient type simulation, pin step is not important, final time is important. Final time means for how much time the simulation will continue. Now our simulation, one cycle is 1 by 100 seconds because period is 1 by 100. So suppose we want 10 cycles, so we would put here 10 by 100, so we'll get 10 cycles. If the value of the period of this was different, we would put different value here. It's okay if you don't put other things, but this step ceiling, it's necessary. It's not necessary, but it's required that you put it really low. Why do you want to put it very low? You want to put it really low because this is the value which will be the maximum difference between the time of taking two values. So if this value is low, the curve will be smooth. If this value is high, then the curve would not be really smooth. So at first let us not put anything here, and there is one thing necessary. We have to press a skip initial transient solution. That is, since our capacitor was not charged initially, we are skipping the initial transient solution. After clicking this, let us press OK, close, and let us run the simulation and see what we get. So okay, wait a second, maybe there is a problem with let's change this. 1 by 100 means 0.01, and 1 by 200 means 0.005. Let us save these attributes. Here 10 by 100 means 1 by 10, 0.1. So close. Let's see if it works. Okay, there is just one pulse in 100. So you see what happens is here it's rising slowly, and after one time, after a certain time, it's getting fixed. Now for some reason we are not seeing the fall of it. Let's check why. 0. This is 0.005, 0.01. Save it. Okay, sorry. It would be okay. Save attribute. Okay, and here 0.1. Okay, close. Okay, so just just one thing, you cannot put 1 by 100, you have to put 0.01. So you have to put it in decimals. That's where I was wrong. Okay, so you see the curve. This red curve over here is actually our input, and this curve over here, this is our output. So you see it's gradually rising and gradually falling. So we are seeing too many cycles. Suppose I want to see just the 2 cycles. You see the second cycle ends as 20 milliseconds. So what we do is we double click on this axis and we see something like this. We have x-axis, y-axis, x grade, y grade. So since we want to minimize the x-axis, you see data range, it's given auto range. You press user defined range, and after user defined range you choose 20 ms. So see 20 millisecond, it's for the when the input voltage is high, capacitor is getting charged, and when the input voltage is low, capacitor is getting discharged. So this is how it's the RC circuit is getting charged and discharged. Now the thing is, see, this curve over here is not smooth at all. It's not very good. So what we need to do is we get to transient analysis. We increase the decrease the step scaling to 0.00001. Suppose we close it and we simulate it again. After simulation, if we change it to 20 ms, you see now the curve is really smooth. Now it's for you to play around with the circuit and see how the rise and fall time changes. For example, what happens if we increase the value of capacitor? Suppose it was 1 micro. What happened if we make it 47 micro? Let's see what happens. We simulate it. See, you know what the change is? It's not very visible. The change is the time constant is increasing. It would be more visible if we go to 0.01 micro. Go to 0.01 micro and simulate it. Okay, and 20 m. You see, it's rising very fast. You cannot even see it. It's rising so fast. So the smaller the value of capacitor, the faster it would rise. So if we turn 0.1 micro, it will be rising a little slower. Let's check. So from this experiment we can find out that the so here it's rising a little slower than the earlier value. So from this experiment we can find that the smaller the value of capacitor, the faster it will rise. What happens if we change the value of resistor? What if we make it 5K? Let's check. So see, if we increase the value of resistor, it rises more slowly. It will become clear when we switch it to 20 milliseconds. So it's rising more slowly than it was before. So what happens if we increase the value of R? Then what happens? The output rises slowly. If we increase the value of C, the output rises slowly. Decreasing the value of R and C will ensure that the output rises fast. So this is one of the observations that we get from this circuit. Now what we need to do is, for our experiment, we need to first analytically or theoretically find out what the value of RC time constant is. The time constant, as I said, you'd be learning in theory, tau is equal to RC. So tau should be here, our R is equal to 1 kilo ohm and C is equal to 1 microfarad. So our tau should be equal to 1 kilo ohm into 1 microfarad. That is, if we write it here, our time constant tau is equal to 1 kilo into 1 micro. That is 1 into 10 to the power 3 into 1 into 10 to the power minus 6. That is 1 into 10 to the power minus 3 is equal to 1 millisecond. Our time constant should be 1 millisecond from the circuit. Now what you need to do is, you need to verify it from the graph itself. How you can do that? You draw the circuit where R is 1 kilo and capacitor is 1 microfarad, and you simulate it. After simulation, you'll get a graph like this. After getting the graph, maybe take 2 cycles. So 2 cycles would be 20 milliseconds. You get 2 cycles. Now this is the falling or the discharging period over here, from 5 milliseconds to 10 milliseconds. So you press here toggle cursor and you click on a random point. After clicking on a random point, you take this value. You take the value of this point. Now here the y-axis 2.3049 is the capacitor voltage and x-axis 6.4623 is the time. Now how will you determine tau? You will determine tau from this equation. How? Here Vc is equal to, if you look at the graph, Vc is equal to 2.3049. So Vc is equal to 2.3049 is equal to V in was our 10 volts e to the power minus tau. Now what is the value of t? The value of t would be 6.4623 milli minus 5 milli. Why minus 5 milli? Because it starts to decrease from 5 milliseconds and onwards. So our value of t over here minus t. So the value of t over here would be 6.4623 minus 5 whole into 10 inverse 3, because it's in milli. So if you modify it, if you divide this thing by 10 and take ln and find the value of tau, you will find that tau is almost equal to 1 millisecond. Not exactly equal, it's almost equal to 1 millisecond. So this is your experiment. In your experiment, what you do is you build a circuit like this one. Here if you'll build a circuit like this one, from the circuit you'll find the value, from the circuit you'll find the graph that you'll provide in the report, and from the graph you'll find the time constant, and you'll find time constant for 3 different points in the falling cycle. And okay, so from the graph you're finding the time constant, then you have R and C. So analytically you find the time constant RC is equal to whatever that might be. So you compare the 2 time constants, whether they are equal or not. They should be equal or very close to each other. So that is it for this lecture. Thank you so much.